Hi everyone, my name is Liu Yuan. Today my research topic is optimizing vessel scheduling in ports, an integer programming approach to mitigating extreme weather impacts. Today my presentation includes 7 parts. Let's start with the introduction. As we all know, the maritime transport plays an important role in global logistics and international trade. According to reports from the United Nations Conference on Trade and Development, the global maritime trade volume rose to 12.027 billion tons in 2022, with an expected growth rate of 2.4% for 2023 and a forecast to exceed 2% annually from 2024 to 2028. So we can see the resilient support system is quite important. Any disruptions in port operation will exert serious influence on global economy. However, the extreme weather, especially the hurricane, have posed a significant threat to the commercial shipping. For example, the Hurricane Harvey, which precipitated a flood closer to the port of Houston in 2017, incurred an estimated $125 million in the Hartz region, according to reports from the National Hurricane Center. So we can say it's quite important to optimize the vessel scheduling during extreme weathers. To be precise, before the extreme weather, we can consider what is the optimal sequence and the departure time for these vessels to evacuate. And after these extreme weathers, whether vessels will return to the ports and what is the optimal sequence and the departure time. Let's see some related works. As we just mentioned, the vessel scheduling under extreme weather has been explored widely. And some scholars have analyzed the significance of these extreme weathers for different stakeholders, like the governments, commercial shipping companies, and the ports, and so on. And also, some of them formulated some algorithms to predict the probability of extreme weathers based on historical data. And also, they optimize the evacuation routes during extreme weathers. And also, the vessel schedule recovery plan have also been explored. And the existing research have formulated some models to balance the environmental sustainability and the financial performance. For example, Elmi and other scholars have formulated a multiple objective model to consider the carbon emission as the sailing speed reduction incentives to solve the conflicts between the environmental regulations and the operational delays. And for tugboat scheduling problem, from the perspective of the optimization objectives, the majority of research focusing on the operational cost and fuel cost optimization. For example, the ARMOR formulated a model to solve the tugboat scheduling problem, and considering the tugboats run to minimize the maximum waiting time for vessels during the attacking boats operations. And also from the perspective of the optimization methodologies, the integer programming, mixed integer programming, and the Markov decision program process, as well as other algorithms, have been widely applied to solve this kind of problem. For example, Wei have proposed the Markov decision process to solve the tugboat deployments and to overcome the challenges during the tugboat's scheduling problems. So we can see the previous research had considered the single optimization problem. Well, the little attention have been attached to the optimization models with multiple costs. So we want to fill in this gap. Let's see the problem description. In this research, we consider vessels are engaged in cargo operations at the ports. However, at time zero, the port's command center received a weather alarms indicating that a star will arrive at the port at time T1. That means all vessels will evacuate before time T1. So what is the optimal sequence and the departure time for these vessels? To facilitate our research, we define the tugboats as PV and the remaining time to finish the cargo operation for vessel V as TV. And we consider two situations. For vessels return to the port after the extreme weather, we consider the departure time will be later than the departure time when there is no storm, leading to a delay cost, which is denoted by DV. And also we consider that if vessels with little remaining time to finish cargo operation, they may not return to the ports after the storm. So there will be a abandoning remaining cargo cost, which is denoted by CV, where CV refers to the cargo values. Yeah. And then to make sure our vessels evacuate safely, we define the headway, which means the time interval between two adjacent vessels as eta minutes, with the sailing speed as knots. And after the stall, we consider the decisions of vessels, whether they will return to the ports, and if they determine to return to ports, what is the optimal sequence and the departure time for these vessels. So based on the problem description, we formulated an integer programming model. Before introduced objective function, I want to explain some meanings of the some notations. The first is the set of moments as vessels return to the port after before and after the stall, which are denoted by I and J respectively. And also, WV refers to the departure time for vessels before the stall. And in addition, we consider three binary decision variable, ZV, YVJ, and XVI, where ZV equals 1 if vessel decide to return to the ports after the storm, and YVJ and XIV are related to departure time after or before the storm. So let's see objective function, where the function consists of three parts. The first part is the tugboats for all vessels departing from the ports, and second part is the cost for vessels not return to the ports, where we consider the delay cost savings and the abandoning remaining cargo cost. And also we consider the delay cost that's vessels return to the ports. Where we can obtain the delay time by calculating the departure time minus the departure time when there is no stall. And we consider the related constraints. Before the stall, all vessels will evacuate from the ports. Then we assume the adjacent the time interval between two adjacent vessels will not less than 8 minutes. And also, we consider the decision variables domain of departure time WV. And after the stall, we consider the decisions of the vessels. For some vessels, they may return to the ports. Then we will consider the time. We will regulate that the time interval between two vessels will not less than 8 minutes, just like the constraints before the stall. And for other vessels with the smaller time time to finish cargo operations, they may not return to the ports. And let's see some propositions. The first is the departure time for vessels returning ports after the storm, where we can see this the departure time belongs to the cells that's T2 minus T2 plus the times of atom, because the earlier the vessels return to the ports, the less the cost it will generate. And also, we can see the situations vessels return to the ports or not return to ports after the stall in optimal solutions. And we conducted numerical experiments, and in this study, we selected Shenzhen ports and selected 12 different types of vessels, where the eta ATA is set to 5 minutes, and the setting speed of vessels is set to 12 knots. And these are settings of vessels length, delay cost, tugboat cost, and abandoning car cost, and the remaining time. It is noteworthy that the vessel length and the corresponding tugboat cost can be searched from the Shenzhen port's website. However, the TV, DV, and the CV are randomly generated because these data are very stochastic in reality. And then we can see the basic results. Firstly, is the objective function value, which consists of three parts. The first part is the tugboat's cost of 22,000. And second part is the vessels returning to the ports. And last is the delay cost for not last is the cost for not return to the ports. Just like we say in the integer programming model. And the departure time are times of eta because we can calculate the latest departure time in this model. We can calculate 120 minus the average sailing time. And we find the latest departure time is v minus 1 times eta. So that's why the departure time belongs to this set. And also, the vessels with a larger TV may depart from the ports earlier to make the vessels with a smaller TV can finish the cargo operations. And finally, for vessels return to the ports, a larger TV will induce a larger WE, and they will return to the ports earlier to minimize the delay cost. And also, we conducted sensitivity analysis, where we consider the impacts of PV, CV, and DV variations on optimal decision. And through the sensitivity analysis, we find that the variations of DV affects the optimal decision greatly, while the variation of PV exert minimal influence on the optimal decision. And also, we conducted a robustness analysis, and we find that with the variation of PV, CV, and CV and DV variations, the optimal objective values changes less than 5%, which demonstrates the robustness of our model. In summary, through the basic experiment analysis, we find the departure time of vessels belongs to this as times times of eta, and a larger TV will induce a smaller WV, and for vessels return to the ports, the higher DV will induce the larger WV, and the departure time for vessel return to the ports after the will earlier to minimize the delay cost. And through the sensitivity analysis, we find that DV affects optimal decision greatly. And through the robustness analysis, we find although the PV, CV, and the DV varies simultaneously, the changes of optimal objective values is varying is less than 5%, which demonstrates our model's robustness. And in the future, we will consider more uncertain factors as considering the advanced port channel dynamics, apply it in the large-scale analysis in the future. These are references. That's all. Thank you.